Okay, this is notes page 184, and we are doing two sample proportion confidence intervals. And this video will be only on the two sample proportion confidence intervals, and it'll be scenario one. So basically, the purpose is you have two proportions, and you're looking to see if there's a difference. You're trying to find a plausible range for the difference between the proportion of two independent populations. When we've done confidence intervals before, we have our best estimate, and we said plus or minus the margin of error. So when we did them before, we did two samples. We did them for means, and we either had something that looked like this. We had X bar 1 minus X bar 2 plus or minus Z star, and then we had standard deviation of 1 squared over N1 plus the standard deviation of the second one. And what we more focused on, that was if we knew the population standard deviation. What we really focused on was this, X bar 1 minus X bar 2 plus or minus T star S1 squared N1 plus S2 squared N2. So that's what we were using before. And that's when we were working with means. But now we're working with proportions. All right. So we need to go back and think about what we're doing with proportions. First off, I want to remind you that a proportion is basically, or the sample proportion is P hat equals X over N, where X is a number of successes and N is the sample size. And it's not surprising that since this was our formula before, where we had the sample mean and the two sample means, we're going to have two sample proportions. All right. And anytime you work with a proportion, it'll be a Z. There'll never be a T when you're working with proportions. It'll never happen. It'll always be a Z. So P1 hat 1 minus P hat 2, the first proportion minus the second proportion, plus or minus this critical value Z star. And then this will be our square root, our standard error. And what's interesting about that is it's almost the same thing as we had over here. And when we were working with a one sample proportion, all right, which I know we just talked about the other day, it looked like this. Our formula was P hat 1, we only had 1, plus or minus Z star. And we had P hat Q hat over N. Well, this looks almost exactly the same, except because we have two proportions, we have to have two of these underneath the radical. So almost the same thing, all right? Don't need to worry about the variance, all right? You do need to know the critical value, standard error, or this whole thing together that I'm circling is known as the margin of error. And you need to know that this part right here, the difference between the two, makes up our best estimate. That's our best guess if we only could choose one number. But we're going to choose a range of numbers because we're more confident with a range of numbers. I'm going to leave the rest of this for you to read. And then we're going to take a look at the recipe for success. Well, not surprisingly, as we've done before, we've started off by defining P1 and P2. P1 equals the true population proportion for whatever the first one is. P2 is that let P2 equal the true population proportion for whatever the second one is. Conditions. These are the conditions you need two independent random samples. NP and NP has got to be greater than 10 for both, and NQ has to be greater than 10 for both, and it needs to be less than 10% of the population. We will do this because this is basically a check to see that we can do the problem. This gives me normality check, and we're looking to see whether or not our samples are large enough. We're looking to see if our samples are large enough, and we will do this for both proportions. All right, checking to see if samples are large enough. We'll write the equation. We'll list all of our values that we're going to plug into the equation. We'll go back and calculate T star, which we've been doing, Z star, and we'll like we have over and over again. And usually we're just plugging in, if it's a 95% confidence interval, it's going to be 1 minus 0.95 divided by 2, and mean of 0, standard deviation of 1. This is where we're going to run it on the calculator. And our conclusions look almost exactly the same. One thing I want to point out is we've added this little bit at the bottom to help you out. If 0's in the interval, we're saying there's no significant difference. If it's not in the interval, there is a significant difference. So let's give this first confidence interval a try. This is scenario 1, and it's essentially on what is numbered on your page as page 186. So a grocery store manager in a simple random sample of 85 people going through the express line, that only 10 paid with checks. And then we have a simple random sample of 92 customers passing through the regular line and 37 paid with checks. Construct a 95% confidence interval for the difference. So we have a simple random sample here, and we have a simple random sample there. And you're like, and you may be trying to make a decision. You go, hey, you know what? Should I be doing proportions or should I be doing means? And if you're not sure, this will help you out. If it's going to be one with means, they're going to either have to give you the standard deviation of the population or the standard deviation of the sample for both samples. They give me a simple random sample, and I don't have that. They did not give me a standard deviation. Because there's no standard deviation, I'm going to have to use proportions. So what was the very first thing on the recipe to do? The very first thing on the recipe said, define P1 and P2. So let P1 equal the true population proportion of people paying by check in the express line. And I'm just going to tell you right now, those people are evil. You do not pay by check in the express line, and you should not be allowed to use coupons in the express line. I'm just saying that's just wrong. Never do that. If your parents do that, talk to them about it, get them squared away. All right. I'm going to go ahead, and even though this isn't part of the first one, but I just think it's a good way to organize, I'm going to go ahead and put P hat 1 equals X over N. Well, I had 10 people pay out of 85. So P hat 1 is 10. So just so we have that information, very easy to find, 10 divided by 85 is 0.11764. And you don't have to do it right here at this point, but I think it'll help you out if you do take the time. I think it'll help you out in your organization is to go ahead and do this right there. So P hat 1 is 10 over 85, which is 0.1176. Now we need to do P hat 2, or P2, to find P2. So let P2 equal the true population proportion of people paying by check in the regular line. I don't like people paying by check in the regular line, but that's okay. They got to buy it somewhere if they're paying by check. All right. So they should go in the regular line because that's not the express line. Okay. So here we go. P hat 2. In this case, we have a simple random sample of 92 and 37 paid. So 37 out of 92. Now, I don't think there's that many people paying by check anymore. But it does happen. I know this is kind of an old example, but here we go. What we have to work with. All right, so we've defined p hat. We have p hat. We know we've defined p1. We've defined p2, and we actually know what p hat 1 and p hat 2 are. The next thing was write the conditions, but the only thing we were going to check is we were going to check the normality condition to see if it was normal enough to actually use a z or to use the normal. So we're going to have to go. All right, we're going to have to do for p hat 1 and for p hat 2. So we're going to go n1 times p hat 1. That has to be greater than or equal to 10. And then n1 times q1, q hat 1 has also got to be greater than or equal to 10. And just as a reminder, q hat equals 1 minus p hat. All right, so here we go. Let's check this out. Our sample size for our first one was 85. And we said 85 times, what was p hat? 0.1176. And if we do that, we actually end up getting 10. And that's big enough, barely, but it's big enough. We do the next one, it's 85. Q hat is going to be 1 minus 0.1176. And that, when I multiply that out, I end up getting 75. Please make sure that you subtracted before you multiply. And you go, okay, well, they're both bigger than 10. All right. Then we need to do, so we've done N1 and N2. So this is for the first one. Now we need to do the second set, which is going to be N2, P2. I need to put my little hats on, cover all the bald spot that I have. Like, you don't have a bald spot, you're just bald. That's fair. So N2 and P2 also have to be greater than 10. And when I multiply, I'm going to end up with 92 times 0.4021 equals 37. We can check that off. That's greater than 10. And then we can go 92. Remember, oops, this should have been a Q hat. That should have been a Q hat right here. 1 minus the 0.4021. And we should have gotten 55. And that's greater than 10. So both samples are large enough to use the normal. All right. So we've done our conditions. We're going to go ahead and write our equation. And our equation is this big thing that makes us look really smart when we know how to use it. P hat 1 plus or minus, can't even write the equation. P hat 1 minus P hat 2 plus or minus Z star P hat 1, Q hat 1, N1 plus P hat 2, Q hat 2, N2. All right, so I'm going to start plugging in, and I'm going to plug in below this thing. Well, we already said P hat 1 is a 0.1176, 0.1176 minus 0.4021 plus or minus. We're going to leave a space for Z star. We'll calculate that separately. And P hat 1, Q hat 1 over N1. So this is going to be 0.1176 times 1 minus 0.1176 over N1. And our sample size was 85 for the first one. Plus a big radical. All right. 0.4021 times 1 minus 0.4021 over 92. All right, so that's our equation, but we need to go back and calculate z star. Well, I need to know what they wanted. They wanted a 95% confidence interval. So that tells me what I need to use. Because it's a proportion, it's always going to be a normal. So we're going to go second vars, inverse norm, parenthesis 1 minus 0.95, close parenthesis, divided by 2. Mean is 0, standard deviation 1. And we end up getting 1.9599. And if we had to multiply and do all this stuff, that'd be a lot of work. And we can, you can do it by hand or using the calculator, but we can actually do this fairly easily in the calculator. So we're going to go stat, arrow over the word test, and then we're going to scroll way down. And when I mean way down, I think we're going to go down to like letter B, and we should see 2 proportion z int. All right, 2 proportion z interval. We're going to press enter. And our x1 value, well, we had 10. Our n was 80, our sample size was 85. Our x2 value was 37. Our n2 was 92. They said do a confidence level of 0.95. And we end up getting this interval. So we need to write down our interval. And our interval is negative 0.4059 and negative 0.1632. This is my lower bound, and this is my upper bound. I guess none of that showed up. So there we go. All right. Now, I want to back up just a moment. I want to put a label here because this is going to help us out a whole lot. So please go back and do this. We subtracted P1, and P1 was express. So we went express minus the regular. And if you just want to put E minus R to remind yourself, that's great. But you should always label those so you know which one you did. You just go E minus R, something that helps you out to know what you just did, okay? All right, so a couple things. I notice 0 is not in the interval. So that's going to be significant, all right? So let's go ahead and write our conclusions up. I don't know if I'll have enough room on this paper, but I'm going to try anyway. We are 95% confident that the true population proportion difference of those paying by check express minus regular. Now, if you want to say, you can say the true population proportion of those paying by check in the express line minus those in the regular line, but that takes a lot longer. But if you just say paying by check, express minus regular, pretty quick. Lies within the interval. And what was our interval? Negative 0.4059 all the way up to negative 0.1632. So what does this really mean? Well, we went express minus regular. So it's like, oh, there's 40% more who pay in the regular line to maybe just 16% more. And why? How do I know that? Because I went express minus regular. So because it's negative, Because it's negative, I know the regular has to be greater than the express. So because it was negative, this was E is less than R. So 40% less to 16% less pay by check in the express line than in the regular line, or 40% more pay by check in the regular line than they do in express line. So anywhere in those things in this, so I know the express is less than the regular because this is negative. All right, because it's negative, express is less than regular. So what conclusion can I make? Well, the conclusion I can say, or not conclusion, what is the significant? So 0 does not lie within the interval. There is a significant difference. All right. And we actually know one other thing. Because the entire interval is negative, we believe more people, more pay by check in the regular line. Or you could say less pay by check in the express line. More pay by check in the regular line, or less pay by check in the express line. They both mean the same thing. You only need to say one of those. All right. So if they just ask for the conclusion, this is your conclusion. Is it significant? Well, does 0 lie within interval? If it lies within the interval, it's not significant, but since it didn't, there is a significant difference. And well, if there's a significant difference, which way is it? Because it's negative, more pay by check in the regular line. If it's less than or less pay by check in the express line. All right, that's the confidence interval. Thank you for watching that. I'll do a hypothesis here in a moment.